I don't know what everybody else's experience in this room is reading through these notes. I'm hoping that people are reading them because I'm not going to be trying to cover every little detail, but I'm going to be going through them relatively carefully and thoroughly. And the main reason I say I don't know what anybody else's experience is because I know I'm coming at this from a very different background, right? So if this looks completely, if my talking through all this looks completely bizarre to you, I apologize. If there are things that I'm absolutely not addressing and you have questions about, feel free to yell and I'll try to sort of course correct. But the other thing that's weird for me about going through this material is I can't remember the last time where I've tried to explain or teach or talk through something that I don't understand the big picture of. Like, if I'm ever teaching a class or giving a talk or anything like that, it's always, I know how this is fitting into some broader thing and I can explain that and I have that, I have that sort of context. I can't deliver that here at all. Because, and this is, you know, for me at least, a lot of what I'm doing as I'm trying to read through this is just sort of learn the basics of how this works. Because for my experience, a lot of the time, if I'm sitting there and learning the sort of the basics, the mechanics of how something functions, then after I start getting a handle on that, I can start seeing how it fits into bigger picture stuff. So this is going to be more disorganized, and when I see bigger picture things, I'm going to try to mention them, but I'm uncertain of them. I'm also happy that James is back in the room for this, for me going through this, because then you can say, wait, that's just complete nonsense. You just said something that's false. So please just interrupt or yell. But yeah, so last time I went over, 2.5 pages of this is what we're thinking of when we're talking about proposition versus formula versus judgment and all of that. And again, he's completely obliterating all those distinctions. In fact, even when he uses the phrase proposition, like, his use of the phrase proposition is, as I mentioned, sort of in line with what some other people might say is a formula. He even says, early on, proposition here, then that word got replaced with the word formula. And I mean, it's true. If you go back and read Principia, you see him talking about propositions and things like that. But one other thing that's important about that is that propositions have structure for him, right? He says, as he says, I mean, he does mention this at one point. He says, for a standard treatment of logic, propositions aren't inductively defined. You're not constructing them inductively. You construct the formulas inductively, but the propositions are just sort of something that are floating around out there. And all of that is sort of being run together. Again, not badly, not incorrectly. It's not a bad thing, and it's clearly intentional. And reading through this has given me some better understanding of why this is cool and why he's doing this, which is really awesome. But it's just worth keeping that in mind. So he starts off by saying, one thing I appreciate about this is he's always explaining why we're doing everything, why he's doing everything. So he says, okay, we have 4 kinds of judgment that we want to talk about. But why do we care about having these 4 kinds of judgment, understanding them? Well, because we need those 4 kinds of judgment to explain certain rules of inference. And why do we need to explain or justify rules of inference? Well, because we're not just making up random things, like I was talking about last time. We're not just making up rules for manipulating symbols. These are supposed to be rules of inference that actually correspond to something real, right? So here, I'll rewrite this one. If I get a pen here. Right, this was just the one, just sort of have this here. So he says we have to justify all our rules of inference. So the only way you can do that is explain how the conclusion follows from, or yeah, well, I'll say follows from the assumptions, right? So how the thing down here follows from all the things up there. Okay, so right off the bat, that's why we're doing any of this. So now we've got 4 judgments, right? We have 4 types of judgment that we're gonna start with here. We have A is a set. We have A equals B, right? A and B are equal sets. We have A is an element. Little a is an element. I'm having trouble with my writing right now. Is an element of A, and then we have little a equals little b, and they're both elements of the set A. Right, so we have the statement or the judgment that says A is a set, and then we have an identity statement for those 2 things, for things of that, for sets. And then we have little a is an element of or is in the set big A, and then we have an identity statement for elements as well. So that's sort of why we're talking about these things. And he says there are presuppositions that are going on here, right? So I don't know if this is going to be a useful way to think about it, but this, A equals B is presupposing that A is a set and B is also a set. Little a is in A is presupposing that, right? And you can think of A and B are A and B are equal is presupposing that they're both in A, which is presupposing that A is. I believe I can state that, right? Yeah, okay, good. So, the errors here are sort of a presupposition. And of course, those are all things that you would have to establish before making one of the other claims. You can't just say A equals B, or A and B are equal elements of some set A until you've established A and B are actually elements of that set and that A is also a set. Okay, so then he starts talking about these different types of judgment, right? And these 4 different types of judgment and how we can interpret them, how we can think of what they mean. And he says, let's just focus on these first 2 here. So if I want to just look at, what just happened there? Let's do this. I just want to look at those 2, right? The idea is we can interpret those judgments as meaning different things depending on how we're going to imagine what a set is, how we're going to imagine what the elements of the set are, and so on. So obviously we're talking about sets and elements, but another way of doing this is going to be saying something like this. A is a proposition, and then if that is sort of what we're talking about when we're talking about being a set, if we're talking about a proposition, then this one might look a little weird. Or at least, it looks weird. I mean, it's a sort of thing that's going to look weird at first. And I guess I'm immediately going to jump out of the direct order of things in these notes. But the idea here is that if we're talking about, propositions, so we're imagining the sets are propositions, then when we have this statement here, what we're saying is little a is a proof of the proposition big A. So I know I mentioned at the very beginning of last time that the notion of a proposition is something that has lots of different definitions that you run into lots of places. And it was at the very end of last class, I think after I even stopped the recording, I was like, oh, hey, wait a minute. Also kind of cool is after I just did all the setup about how there's so much different discussion about what propositions are, hey, he's actually providing a definition of what a proposition is. And the definitions he's providing is that a proposition is just a set, right? Because we're just saying it's a set. It's a set of all the different possible proofs of that proposition. So, for example, if you wanted, I was talking about like the proposition that snow is white. Well, it would be everything that would count as a proof of the proposition that snow is white. If you're curious, this has sort of strong history in certain areas of philosophy of language where this notion of verificationism or a verificationist understanding of meaning, which is that you don't get to say what a sentence means unless you can say what it would mean to prove its truth, or what it would mean for it to be true, or what would make it true, right? And the idea of intuitionism in mathematics, the idea of looking for constructions. One of the other things he's going to talk about is that we can use the word construction instead of proof here. So you could think of A not as a proof of it, but rather as a way of constructing whatever this thing is, this proposition. Okay. And there's other ones he mentions. You could think of this as saying big A is an intention, and then little a is a method of achieving that intention, or big A is a problem, and little a is a method or a program for solving that problem, right? There's lots of different ways you can think of. Here is a thing, and then all the little parts are different ways of doing that thing, or constructing or building that thing. Okay. So that's sort of a way to think about what these things mean. But now we want to say, how do we actually interpret them? How do we actually think about what these judgments? How can we explain these judgments, right? So he says, all right, well, here's one way to think about defining a set. Let's just focus on the first thing here, right? How am I going to explain a judgment? Remember, explaining something is justifying it. So how am I going to justify my judgment that something is a set? Well, he says one way to do it, you might think, is just say these are what go into it, right? So if I want to justify the judgment that this is a set, right? If I want to say this, that's real ugly. If I want to say that, if I want to explain that statement, right? How do I justify the statement that the natural numbers are a set? Well, here's the first attempt, which doesn't quite work, but it sort of gets the ball rolling. I tell you how to create things in it, right? So I say this gets to be in it, and then I get to say that if something is in it, then so is its successor. I have to actually write in the successor though. So is its successor, right? But he says this isn't going to be sufficient, because here is a judgment that I'd like to make that is not justified by the things that I've written down so far. Right? I can't do that yet. Why? Because the only things that I've allowed myself to do so far are these. That's in there, and that's in there, and that's in there, and that's in there, and so on. And so one thing I want to point out right off the bat is what he's talking about when he, and this is again sort of that smashing together of form and meaning, right? Is that this is not the same as this, right? You do not, like, of course we think of those as sort of, or I would historically have described those as two different strings of symbols, two different formulas or whatever that refer to the same thing. But crucially, they're not the same thing from this perspective. From the perspective that we're working with in sort of Martin-Löf's type theory, those are not the same thing, because the structure of the expression is sort of part of the structure of the thing, or is the structure of the thing. I'm not entirely sure the best way to put this, but I think one way to think about it is we're saying that the elements themselves have this structure that is either the same as or isomorphic to the structure of the string of symbols that we're using to write it down. And so the problem is I have not yet figured out, or I have not yet provided anything in my rules for explaining that statement, for explaining what it means for that specific set to exist, or for the natural numbers to be a set. I have not given any explanation that allows me to incorporate that specific statement. So this is a good starting point, but it's not sufficient. We need to add to that. And so the idea is, what we're going to do is we're going to instead just define canonical. We're going to define canonical elements of the set. So we're going to take this to say how we have sort of canonical elements of the set. So canonical elements are going to be the things, again, element includes the structure of, the structure at least sort of represented by or corresponding to the actual expression that's being used to refer to it. And then we also need to say when two canonical elements are equal. So we'll do that here. And really, again, don't think of this as being like, at least for me, I find it best to not think of this sort of statement as saying A equals B is in A, right? That's not the way to think about it, right? The way to think about that is just A and B are equal elements of A, right? So that's what we're saying here. This is, 0 and 0 are equal elements of A. That makes sense. And then
the notation these days has moved away from the element of altogether to avoid this. So people will say A colon capital A, and then they'll say A equals subscript A.
So, okay, cool, that's helpful. So it would look like
as elements of A
yeah.
are equal.
Right. So it would be something like this.
Yeah.
That's a bad little thing. And then the alternative here would be that and this.
Right. And that way, the well-trained mathematician doesn't accidentally insert a bunch of spurious reasoning.
Based on the idea that there's some set thing when it isn't. Yeah, that makes sense. Okay, so that's cool. Yeah, and that is a helpful change in notation, at least for me, because again, this looks for all the world like you're saying 0 equals 0. Somehow that statement or whatever that thing, whatever that thing is, we don't even know. We haven't defined that at all. But that thing is in A, or is in N. Right, and so then we also have this. I keep forgetting my successor things. Okay, so we have that, right? And now we know how canonical elements can be identical. How do I know this is covering all my canonical elements? Well, because I know that all my canonical elements are going to be things like this. right? Notice that the little a here does not have to be a canonical element, right? We're just saying if you have any element of the naturals, then put a successor sign after it, that thing is a canonical element. So as long as I've got things here, a and b, and they're equal in the natural numbers, then I know how to say that these canonical elements are equal. So that's the idea here. This is something else. Again, I don't know how much of this was obvious to everybody else, but it's something that I wanted, that sort of I paused at, so I'm going to just keep going over the things that I paused at. These are the canonical elements, right? Not the a, just the a prime. And then likewise, these are the identities for canonical elements that we've just defined. Okay, so he goes through some more examples of how to do this, which I'm not going to go through. He talks about sort of a Cartesian product of two sets and things like that. But I wanted to pause just for a second and talk about terminology, because something, at least for me, that I find that I have found helpful in working through these notes to think about is why the word type is getting used anywhere, right? And maybe this makes perfect sense to everybody else in this room, but it's something that I have been wanting to understand and think more about. So, especially when we talk about a proposition is a type, right? Or even just a set is a type. What are we saying here? So, the way I like to think of it is, or the way I've been thinking of it, I shouldn't say the way I like to think of it, but the way I've been thinking of it is, if you just sort of imagine a universe of all the things out there, right? Whatever that means, just all the things that are, right? Well, the natural numbers is the type that corresponds to the things that are 0 and 1 and 2 and 3 and 4 and so on, right? What are those things? Well, what's sort of common among all of those things is they share a type. They share a type of thing that they are. They are a natural number, right? Or a proposition, right? If you think of when we talk about proofs of propositions or methods for confirming the truth of a proposition or something like that, right? There are lots of methods for doing things out there in the world. So if you consider all of those things, some of those are going to be methods for proving that snow is white, right? So what's common among those things is that is sort of they have the following type or the following characteristic, the following property. They are all things that are proofs of snow is white. They could be other things too, right? They don't have to only be proofs of proofs of the proposition that snow is white. But that's one sort of characteristic that they all share. And if you think of a type as something that sort of gathers things together according to some characteristic that they have, that was at least a way that I was finding helpful to sort of think about what's going on here, why we're using the word type. Okay.
I will say that there's also, at least from the intuitionistic point of view, you don't think of the natural numbers as having everything in it. You create the rules for what it would mean to put things in it, and you can build it, and you might have 0 in there in the first place, and then you have 0 tick, 0 tick, tick, and so forth, and you can inductively hypothesize what's coming next. But it's not like the universe had all these out there, and then this cowboy went out and lassoed them all into the thing called N.
Right. Okay, yeah.
From the set theory perspective, somehow everything existed, and then you got to name it. And here, it's more constructive. You just say, what are the rules for putting things into this set? And therefore, you don't have to fathom some of these more questionable things of, is there a set of all sets? Because there's no such thing as a set you didn't make. So you can talk about a type of all types, because you can talk about the types you've made so far. So you have the types that you've made so far, and that's the type of types. And
that
you can build things in a way that doesn't get the logic a little too out of hand.
That's cool. Yeah, no, that's helpful. Thanks. Because, okay, so then the way to think about it is, I sit here constructing some things, and then I decide. This is actually really helpful. Thanks, because this is something that this is a much easier way to put this. So if I can restate that, it's the idea is that if I just sit here constructing some things, and then I decide I want to think of these things as having some sort of similarity or grouping among them, then I'm going to say, okay, these things I call having as having this type, or I create the following type. It's the type that corresponds to these things. Is that? Oh wait. Okay. Cool. Yeah. Awesome.
Would it be correct to say there's some kind of temporal element? You're like, hey, I'm creating these 10 types, and then for my 11th type, it's the type of the first 10 types. That's something.
You could have an inductive type, which means that you build some types or some ways of introducing things, and you add to that list, and then you might create a type from those. So you do have sort of this complexity building up. But at least in constructive models, it's not, the mental model isn't that there exists stuff and I go out and I classify it and give it names, but rather the things I'm going to talk about are the things I've created bubbling up from the surface of like a few assumptions at the beginning. You do need to still have axioms. There are still, like, how do you get off the starting line? You need some basic language and some rules like weakening and stuff like this. So there's some basic things that you do still start out with, and then you get to start writing out your instructions from those axioms.
If I, so would it be then correct or suitable to think of those axioms as basically saying, I'm going to restrict the things that count as constructing types, or the thing that counts as constructing things, really?
Yeah, I mean, restrict, yeah, in the sense that you say, these are my abstractions, I'm allowing these particular steps, and I don't bother asking how those are justified. These are my axiomatic truths, like P implies P is, like, the one axiom you must have to build this kind of type theory. And you don't ask why does P imply P, you just say it's an axiom.
Right.
Why does 0 equal 0? Because I said so.
Right.
And then you don't get into these parables that go on forever, wondering how you get started.
So, if I'm taking that correctly, then what we could actually say is this is an example of that.
Yeah.
So this is something where I'm not explaining why that's true. I'm not saying here I've constructed things in such a way that definitely makes this true. I'm saying this is one of the things that I just accept as a thing that is.
Yeah. So in sequence calculus, you put like a turnstile in front of it with nothing in front.
Right. Yeah.
You just say, I don't need any reason.
Right.
It's just an axiom.
Right. Cool. Okay. So I wanted to talk about these different proofs of various propositions. That's sort of the next thing that's coming up. We're talking about a proposition, right? We're saying that a proposition is identified as its set, or the set or type of its proofs. Now, going off of what James just said, I assume that I can then say, the idea is I'm going to somehow build up things that count, somewhere off in wherever. I'm going to build up the things that count as proofs of propositions. And then I'm going to collect those into various types, saying, well, these have this similarity, and I count these as together and these as together. And I have rules for creating new proofs out of old proofs. We're going to see that in just a second. And then those are the things, the collections of those into types is what gives me the propositions. Okay, question then. I have a genuine question here then. What would, so there's this sort of chicken and egg thing that I start getting stuck on here, right? Because I just said, you're going to start by saying, here are things that count as proofs of propositions. But we can't say that until we have the propositions. So is it really just a better way of saying, like, here are the things that I'm going to count as proofs. And then I'm going to collect those things together and say, okay, those collections are propositions. And then I can sort of derivatively say that a proof that is in a proposition is a proof of that proposition. Is that a way of thinking about it?
So a constructivist wouldn't think that the proofs existed before.
Right, no, I'm creating them.
Yeah, you're creating them. So you would say that the claim I'm going to make is that A plus B is equal to B plus A in the natural numbers.
Mm-hmm.
That's a theorem I'm going to declare. Right? So you can declare that statement, and that's a proposition, or what's called a mere proposition. There's a family of propositions that happens later on. So the ones you're describing are called mere propositions, because mere propositions are propositions that have actually only one proof. So they're not the collection of all proofs to be had that somebody will ever fathom. Rather, you're saying, I declare there to be one piece of evidence for this. And so the evidence you're going to get for this, I claim, is whatever evidence you had for 0 equal to 0. So that's called the reflexive evidence.
I just want to interrupt for briefly.
Sure.
Can I write down the thing we're talking about like that? Is that the correct way to write it down?
Absolutely say, that's a prop.
Okay, that's sort of the starting point.
Yep, and so there's going to be a type called prop, and you just made a proposition. Now, that proposition, that particular A plus B equals B plus A, is data of type prop. But it also is its own type. It's like a set of sets, right? So it has evidence, or it doesn't. It could be the empty set, right? We just don't know if that proposition is true or false. And this is where, like, you have to be careful with who you talk to. If I make a proposition in a paper, I'm telling everybody, I think this one's true. I'm not leaving it open to debate. Whereas in type theory, when you say it's a proposition, you're making no claims of its validity. That's to come later. So here is a proposition. We propose that A plus B equals B plus A. And it's going to be a mere proposition because at the end, if it's true, it'll be given by one proof, exactly one proof.
Okay. So
we could give that proof.
sorry, I'm pausing here because I'm like, okay, so what does a proof look like? Is it just going to be so one of the things that I've known, I mentioned this at the end of the last class as well, after, or the last, whatever, this is not a class, the last meeting. Anyway, yeah. That one of the things that I really thought was cool about this, as I was sort of flipping through it, was that later on I saw, okay, he'll give, you know, one of these like trees of steps, right? And and this is the exact same thing that was just written before in 2 English paragraphs. So rather than trying to write up the formalized version, you know, we could just, the idea is we can think of the proof, the single proof you're saying that corresponds to this particular proposition, or is this proposition, is going to start, you said, is going to start by saying 0 equals 0, and then sort of build up off of that to say, eventually we can build up to, we can build off of that fact to know that, you know, A plus B equals B plus A, because we know something involving, yeah, and I mean, I won't bother trying to write that down. I imagine that it would not be.
It's not instructive. It's just everything is boring. But,
right.
But you realize that at the end of the day, this is why you know this to be true, is that a bunch of smaller steps got you there. And you walk your smaller steps down the road until you got there. And what this technique says is that you want to take the concept of, say, implication and treat it like a function.
Yeah, we're getting there next. Yeah. Okay, no. Okay. Well, yeah, we'll get right there next. Because that was sort of what I thought was another really cool thing here. Okay, so we're just to sort of reiterate then, or to make sure I'm getting this. The idea is we're going to have some rules, or we could have some rules. We don't need rules, but you know, following in the sort of way that this is the way that these notes are going, we could, and in fact I suspect at some point will, or easily develop the tools to develop rules that allow us to finally say that at the end of some derivation. And it might even, if I'm right, let's suppose we're just dealing with natural numbers, look like this in his notation.
Yes.
Okay. And then you're saying in more modern notation it would look like that.
Yes, and it would also have some sort of quantifier for all A and B.
Right, yeah, there's some sort of quantifier in front saying that, yeah, for all A and B.
So in the notation that's here, it's not for all, it's a pi symbol.
You
think of it as the for all.
Right. And so the idea is we'll have that, and then we'll have something, some other, I guess, introduction, or I forget what it's called. I don't think it's whatever. We'll have some other rule that says why we're allowed to go from that to this. Right? Is that correct? We'll have something that says, okay, given that I've now proved, or got a proof of this, I don't know. This is where I'm getting stuck. So,
the type.
Yeah, the type prop. That's what I'm wondering about.
Actually, just what you would consider a subtype, meaning of all the possible types, the ones that have a single element are called propositions. Any type of data in the world that only has one element in it is called a mere proposition.
A mere proposition. And then we know how to.
It has one element.
Right.
Because it's going to come from there's only one piece of evidence for 0 equal to 0.
Right.
And it's an axiom.
Okay.
Law that says I shall be.
Okay.
And you're going to move that piece of evidence and rename it, and give it spray paint and whatever, and it's eventually going to become new looking evidence, but still one piece of evidence. So that whole for all will only hold one proof.
Right.
And therefore it is a mere proposition.
Okay. So more speculation on my part. Would the idea be that this would be like, this piece of evidence could be like a canonical thing, and this would be a non-canonical thing that ultimately constructs that canonical thing? Because it can't be the canonical thing, right?
Yes, that's right.
Okay.
It beta reduces to this.
Right.
Unique
Okay.
piece of evidence.
Because
you have to apply the translation, so it's not canonical. It's beta reduction.
Right.
Yes.
And that was so I'm harping on that because it was something that I saw that, like, you know, what it is to be an element of a set and it is to construct a canonical element of the set. And so there has to be some method, I guess beta reduction, what you're telling us, beta reduction is going to be the method here, that will get us back to that canonical element. So what we're saying here, okay, that's cool.
Yeah, remember we had on the board some time back, we talked about how you could have, you know, like a list of length 5, but then your number 5 might be represented as 2 plus 3, or as the number 5, and then you're wondering, are these really two different data types? And the answer was no, we're going to call them the same, and that's because there's a path to reduce one to the other. In the same way, whatever non-canonical evidence we have, there's a path to reduce it to the canonical evidence.
As an example that I thought was cool and helpful, I'll bring this up. Like I said, I'm really just sort of.
And by the way, I'll just say a word for the mathematicians in the room. At the end of the day, when you write down the path from the non-canonical to the canonical, that's a homotopy. So what's really going on here is we're doing some homotopies between some sets.
So he said this, or he used this as an example, right? And he says, okay, this is a non-canonical element because it does not have that structure. It doesn't have that form. But it reduces to this, right? Whatever. It reduces to that, and that is canonical because it does have that form, right? It has the form of a thing followed by a check mark. So that's a canonical element. So this is, okay, cool.
You got it. That's it. That's the whole thing. Well, you can reduce it to something canonical,
right.
Then it gets to be in there because of this transitivity law of equality.
Right. Yeah. Yeah. Or say that.
Call that. That's the Leibniz law of equality.
This one here.
Yeah.
What I was saying is this. So okay, well, let me see if I can restate the way I was thinking about it, and you can tell me if this is equivalent to what you're saying. This gets to be in there because of that.
Yep.
But this only gets to be in there because of some version of that.
Yes.
Yes.
So
Yeah.
it's a two-step process.
Yeah.
The first one says, the bottom one is in there from the top introduction rule.
Plus, yeah, so it requires that
Apply
fact.
that, which is the Leibniz
Right.
law.
Right.
That says you can therefore transfer the property of being in N, canonical element in N, to anything that you're equivalent to.
Cool.
Or equal to.
Cool. Okay. I want to just pause here. Is this sort of conversation and back and forth helpful for anybody else in the room? Because it is incredibly helpful for me, but I don't want to be wasting literally everybody else's time. Okay. Again, a lot of this is because I don't know what is going to be obvious to other people in the room. I just know what doesn't make sense to me or I want to sort of get my head around. So let's at least try to get somewhere, and we'll get to this sort of proof of these propositions. You know what I'm going to do? I'm going to do something I did last time because I don't want to have to type all this stuff up.
I have to say, watching the video you did this little trick, I was very jealous of your screen skills.
I have become very fond of, I've become very fond of doing all this.
Oh, and not just fond, good at it.
Appreciate it.
I'm fond of this too, and I have no idea how.
What's going on? Oh, no. So, we'll do this.
I'll take this moment to say, please check Zula, because Tatum has sent out a notice saying, send her information. You already talked about that? Yeah.
Nope, I absolutely did not talk about that. So, definitely, yeah.
Send her information she can put on the website so that you can get
No.
and stuff. You're trying to like apply for places, it's good to say you've been involved in the help package.
I guess we don't need to erase that. Okay, so, yeah, we'll make this a little bit smaller, I guess. Okay, so, right, we've got sort of this first table, and I just want to talk through that briefly, right? This is sort of what we've just been talking about, right? We've been talking about how, okay, the false has no proof, you can't ever prove the false. If I'm proving A and B, right, what I have to be doing is proving A and also proving B. If I'm proving A or B, I have to be proving one of them. But this one's kind of cool. So if I'm wanting to prove that A implies B, the way we do it, according to this, is that we prove, or what we say is, if you give me a proof of A, I can turn it into a proof of B. So I have some method or some mechanism of turning or constructing a proof of B from any arbitrary proof of A. Notably, there's no negation in here. I don't think that's an accident. I don't know enough to be able to explain exactly why, but my understanding of negation in like proving things false is not as is sort of going to be, well, I don't know. I shouldn't say more about that.
Negation is used
A implies. Okay, yeah. So that was my guess. So the idea here is that we're going to be able to say negation of A is just this.
Yeah,
Or sorry, yeah, I forgot. He's still using the horseshoe.
Yeah.
He would probably also, in that case, be using this.
Yep.
Okay. So anyway, same thing. And then for universal quantification, we're saying you give me any individual, and then I can prove B of that individual. So the proposition that says little a has the property big B, basically, or little a is an element of big B, or something like that, right? And then if I'm just trying to prove an existential statement, so I'm trying to prove there exists at least one thing, all I need to do is provide you with the thing and the proof that it has the property in question, right? So I just need to give you the A and give you the proof that it has B. Okay. So this one I think makes pretty good sense, right? If I want to say A and B, I just need to give you both A and B. I need to give you the proof of A and also the proof of B. I'll put them in an order because I need to know which one's coming first and second because they do have an order in that and statement. I'm curious about this. Everything else I was able to make sense of, but I don't know what these sans serif I and J are yet. Or I assume they're coming later at some point in here, but I don't understand what they are.
So you have to convert into the left or the right-hand side.
I get it. Okay, so the idea is I need some method for taking a proof of A and converting it into a proof of this thing, knowing that it was the left-hand side that I had a proof of. So I is going to be some method that takes a thing and then says, I have now created the proof of this disjunctive statement A or B using the first side, and then J is the one that takes something and says, okay, constructor proof. Okay, cool. Thank you.
And you have this, for example, in a lot of programming languages. You might have something that's called an either. Something can either be one type or the other. And you'll talk about it being in the left type, meaning it's the one that's on the left, or in the right type. And it's the same idea. You have to build the data up, glue it together as one universal type, but you still want to be able to access that it came from the left or from the right. And these names might change to left and right on.
That makes sense. Cool. Here, right, we're just using lambdas. I think you all covered that on a day I wasn't here. Right, so this is just saying, the method that takes some x and returns little b of x, where little b of x is going to, or little b of a, little b of b, whatever, is going to be the big proof of, or the proof of big B, as long as you started with something that was a proof of A. This is why this is negation, by the way. In case that hasn't been covered yet, I don't know, this might or might not have been covered at some point, but this is why that's negation, right?
Why don't we pause for a second? Does everybody see that's negation? Does anybody have a question on this or any prior thing that we've gone through?
That's a good point. I have not really paused to invite questions. I apologize. Does anybody want to take a stab at explaining why that's negation?
That as a statement is saying a proof of A proves falsity, which feels like negation. If you're not A, then showing A, something should be really wrong. And falsity is pretty wrong. I don't know how much more sophisticated we want to get at.
I think you have to ask your peers if they are convinced that should be negation.
Can you restate that, sorry?
So negation, like we're trying to say not A. So another way to say it is like if A, implying like for negation we want to say not A, and intuitively it feels like that should be, I don't want to say equivalent, similar to saying if you had A you can imply falsity, and that implying falsity is something we don't really want to do. So that feels like a good way to go about it.
So not in this list is a definition of falsity, which is that false can imply anything. Okay?
Yeah.
So everybody accept that rule of thumb, logic, whatever you call it, rule of inference. So false, once you get to false, you can get to anything. So when you think of not A, you might think of true and false, but ignoring that and just saying we're now going to say A implies falsity. It's an implication just like any other implication. P implies Q. And how do you use an implication? You give it a P, and you get a Q, right? So now, if I have A implies falsity, and I have A, right, those are two different things. One is having the implication. It doesn't mean that anything is hypothesis of the implication, but it's an implication. That's the statement. And I have A. Then modus ponens says I have the thing at the end of that. The implication is applied. We discharge that, and we just have the result, which is falsity. Yeah, there it is, on blue. And so now, if we were to rewrite this, this would be same as saying not A and A gives you something false. Which feels like the law of the excluded middle, only we're not making an axiom here. We're not saying this is true of all statements. We're simply saying if you prove the negation of A, then you can't have it be both true and false, because it will lead to falsity. And once you have false, the next law of inference is you can get anything. So one definition of a consistent logic is that you have more than one outcome. Because if it's inconsistent, you get infinity of outcomes. Actually, all outcomes are possible. You can deduce anything because you get to false, and then from false you get to everything. So you only ever have one, everything's a theorem. So logic would be consistent if some things are theorems and some things aren't. Because if everything's a theorem, then it's probably just got false somewhere.
I'm not sure this is the right way to write that.
There's
a better way to write this, I'm sure, using the notation we're using. But I'm not familiar.
No, I think what you wrote is
Okay.
intuitively understandable.
Yeah.
That's the way to think of it. Is that if you get there, you're done. You're hosed. If you end with falsity, you don't have a consistent logic. So this isn't a very good place to end your life. So then that would mean that if you prove something as a negative implication, like A implies falsity, you're not going to find A along the road. Go for it.
I guess this is slightly different than how I was thinking about it, because I saw A implies falsity. There's nothing that is a proof of falsity. So A is nothing. That's kind of the way I was thinking about it. How is that? Where does that go wrong with it?
Well, I don't know what the word nothing means, and so I end up finding myself wondering if I'm using just words that sound better. I'm not saying that's the wrong way to think about it. I think I have a mental model that helps me guide my logic. But syntactic logic, like this kind, asks you to divorce yourself from the model and just follow the symbols and see if the symbols guide you to a solution. And that's not always great because you can get lost in symbols and not know if you've proved anything interesting, right? You've proved something, but you don't know what you've proved. So that's when you put the model back in to see if it makes a meaningful paragraph, right? So you do have to actually keep the model together. But at the end of the day, what this argues for is a completely syntactic proof. Meaning the symbols followed the rules, and they got to other symbols, and they ended with symbols, and they don't have to have any meaning, just like Dustin's previous talk, where it looked like just gibberish of letters that made more gibberish of letters, and it wasn't until the end that he said, by the way, this is and some other things, that you went, oh, okay, I kind of believe that, you know? So you had no reason to think anything of those sentences until he interpreted the semantics. In the same way here, until you think of that A implies falsity as not A, you think, I don't know, whatever. But then you're like, hey, that's what I do mean by not A. It means that I don't ever have A there. Because if I did, I get to something false. And then it decodes it.
I'm going to jump in and say a couple things here that are potentially on the same. Well, I'm not saying better. I'm not going to say that. Because so everything James has said is correct. And I think everything you said is also correct, Luke. And I think sort of from the way I've been reading the Martin-Löf notes, that's sort of the way he would want us to think about it, or that's the way this would work. Now I get what you're saying, James, that what the heck is nothing. I don't really, we don't know what that is, but right, the idea is we've defined that symbol and sort of in the idea of where we're in the idea of these notes where we're defining meanings as we're going, where we're introducing the meanings as we're going, so we can use these symbols with their associated meanings. That has a meaning of something empty. Right, roughly speaking, there's nothing that or another way to put this, that anything you give me. Remember, we've got we talked about how we can construct all these different proofs. We're going to say that no matter what proof we construct, it's never a proof of that symbol. It's never a proof of that proposition. And then to prove this proposition, or what does this proposition mean, right? Or to prove this proposition, well, we've been told what that means. To prove it, we have to give a method that takes a proof of A and turns that into a proof of this. Well, the only way we could give you could give me a method of doing that is to say, if you give me some purported proof of A, this is where we have this sort of idea of reductio ad absurdum, or proof by contradiction, or indirect proof. It goes by thousands of different names. But the idea is, you assume A, you find out that leads to a contradiction, then you could say, oh, A can't be true. This is, I think, one way to put this is sort of codifying that idea. Because the idea is, what you're really doing when you do this is, if you give me a purported proof of A, I can construct from that purported proof of A proof of a contradiction, a proof of falsity. The only thing I don't know how to make sense of in that yet, from reading these notes, is this notion of a purported proof of A. I don't know what that looks like. So I'm going to be honest, that's like, for me, that's just a black box that I'm waving my hands at right now, in the context of the notes here, and the type theory and the logic being developed here. But that is sort of the way I was thinking about it. Does that comport with your basic understanding of what's going on here, James?
Yeah, you have to be a little bit careful, because this language of logic is compatible, and in fact designed for intuitionistic logic, where it doesn't have the law of the excluded middle. So
Right.
You have to do a proof by negation rather than a proof by contradiction, which is a subtle, only the experts could ever care kind of thing. But it is instrumental here that we say that correctly.
Okay, so I think what you're saying is what I meant, and maybe this is just a difference in terminology. My understanding of intuitionistic logic is you're allowed to do this, right? If you can show that A somehow leads to a contradiction, then you can conclude not A. You're allowed to do that.
Yeah, well, because all you did was prove an implication.
Exactly.
So you make an assumption that you then discharge, and you have the
Right,
implication.
yeah, exactly. So that's fine, and that's what I'm calling proof by contradiction.
Yep.
Or actually that's what I'm calling like reductio ad absurdum or negation intro. But the thing that you can't do, you can't do this. That's what you can't do in intuitionistic logic, right? And the reason you can't do that, well, should be obvious at this point, right? I haven't now, just showing that any construction of this gives me a construction of that has not shown me how to get a construction of A, right? I've just shown how to turn constructions of the negation of A into nonsense. Another way to put that, I did not mean to do that. Another way to put that, as I understand, again, this is going back many years now, to when I first, this is just one of those ideas, but I'm pretty sure this is right. One way to think of intuitionistic logic is that this is allowed, but this is not allowed. You can't do that, which again is just another way of stating what I just said up there about because what is this? This is a method of turning any proof of negation A into a proof of falsity, but of course there's no such thing, so there can't be any proof of negation A. But a lack of proof of negation A does not give me a proof of A. Okay.
I mean, that property is desirable because that's in the model. So
I'm sorry?
that property is desirable anyway. 'Cause
This
that's in the model.
this model or
Yeah, like
this?
we want that to be true or not.
Not if you're an intuitionist. You do not want that. So for intuitionistic logic, you don't have that.
If I can make an observation, so lack of proof of negation of A is not necessarily a proof of A, in part because of, well, we've already said there is something that has no proof to it. So like how our system is created, just because there's no proof doesn't really mean much.
Sorry, when I was saying that property, I was saying the negation of that you not something.
Oh.
Double negation doesn't
Yes.
apply.
Yeah, yes.
Because that's what we're modeling.
Yes, yeah.
let's
Not having that here. This is a desirable property of the system we're defining. Yes, exactly. Yeah, yep, absolutely, yeah.
And you shouldn't panic, because what Gödel showed us is that anything you want to say with that property, if you thought that was true and had to be true in your life, if you cared about it, nothing intuitionistically could counteract that. So you can in fact prove that it's not true, meaning that you can prove that it cannot be contravened in intuitionistic logic. So you're not going to poke a hole in math intuitionistically. But when you make something intuitionistic, because it's a simpler model in classical logic, you will prove theorems that apply to broader classes than is limiting by the classical model. And it's also a kind that has been shown by a very powerful theorem called Curry-Howard isomorphism to be one that a computer can actually do. So what you're doing is you're saying, okay, maybe computers will never be as smart as me, but how smart are they? And the answer is pretty darn close to what you could do. The only things they can't do is this leap of faith that a double negative is enough.
There was something else I was thinking about as we were talking about all this, and I've completely forgotten it, so we're also out of time. Oh no, don't apologize. No, I did not mean that in any sort of negative way. like I said, at least for me, having the conversation about this is far more helpful than just me talking. This is like I said, also like something where I don't have the big picture yet.
Now, if you were to look at like an undergraduate textbook on introduction to proofs for mathematicians, what would you probably see for all these symbols?
Implies symbols.
Like, what were you probably told implies was?
A implies, well, I mean, in, like sector, you interpret that as B as a subset of A.
You probably had a truth table, right?
Sorry.
You probably had a bunch of true falses. If P is true, and you have an imply symbol, and you have Q can either be true or false. Which is the answer? True. Right? So all of these have a truth table when you think of Boolean logic. Maybe we should do one. I don't
Yeah.
pick anyone to write.
There are many different ways to do truth tables. I'll write two that are very different, and I think sort of the two sort of easiest ones to see. This is one way of doing it. And this is the standard truth table for material implication. And then the other one would be this. All right, this is how you do it. All right, then you go true. I probably should put P over here. True, false, true, true. So there's two very different ways of representing the same basic idea.
So this is how at least I was introduced to these symbols when I first was shown, is that people put a bunch of true-false descriptions everywhere. And what this does is it bakes into the formula this excluded middle idea. Things have a value of being true or false, and they aren't allowed to have this middle ground of we don't know. If you look at the formulas up here, though, this is how I actually make proofs in my own daily life. I think that I had a reason to understand A. I had proof and evidence for A. It was in this book, and I just cited what page it was on even. It's not like it's just true and I'll never know why. It's like, it's there. There's evidence for A. And then I'm using that evidence to make evidence for something like A and B. If I'm using P implies Q, I'm assuming evidence for P. That part, the assumption, is a variable assumption. I don't know where I'm getting the evidence from because I'm just making an implication. So I assume evidence, and then I get that from that evidence I could construe it and rewrite it to get Q. So what really Martin-Löf is getting at, what the intuitionists tried to push, was that the proofs matter. Truth tables say the proofs don't matter. It's just about what true or false is. And you don't have to know why it was true or false. You just need to know it was true or false, and then you get the next true or false. And you basically delete your proof as you go along. And at the end, it's enough to just say it's a theorem, and the proof need not be included. Whereas the intuitionists say, well, but look, come on, the proof was how you got here, and there's a lot of information in the proof, and we should maybe look at the proof and store that information. And that's the idea of propositions as types. They're types of data. The data is the proof, or the method you got there. And so what I think is actually happening is it's just people being more honest about what they actually think. We don't really think in true and false. We think of the proof being, because it was even, I can write it as a sum of two identical numbers, and then I can do something else and keep going. I don't really think it was true, and therefore the next thing is true, and I don't even register how I got there. And so having an implication be a function that takes the information P and converts it to Q is how a lot of actual proofs happen. And when it gets to things like Gödel's incompleteness theorem, all of a sudden you don't feel like the world has fallen apart. Because, yeah, of course there's things that you might not be able to get a path to. You don't make an assertion about them being true or false because you haven't made an assertion about everything having a truth or falseness. You just simply say things that are theorems have a proof. And so you can have statements that are in this language that you just don't approach with a proof. And you don't feel like, how can this be true and unprovable? There's no, like, the carpet pulled out from underneath you. But you have to accept that the law of the excluded middle isn't your friend anymore. And some people just like that more than they like establishing, hygiene somewhere else. So you're not going to make everyone happy at once, is the point.
We're real running over, but no, that's fine. We're running fast. I wanted to add one final thing just because it was something, I remembered what I was thinking about before, which is that there's one other thing that I think is just worth mentioning, which is that whenever you're developing a system like this, the notion of a contradiction is also not something that's like baked into it, right? We get to decide that. And so, I mean, in this case, we're basically saying that is the contradiction. And so if I can turn something into a proof of that, what I've done is I've shown this other thing is also a contradiction. So what James was talking about before was sort of a way of thinking about why those two things make up a contradiction because we've defined it like that. If you go to like the system that I was talking about last time, the way things tend to work in that sort of context is you actually just say a contradiction is anything of this form, right? If you have those two, so you say, okay, I say a system is contradictory if it has those two things as theorems for any formula phi, and then you have to say something else to show that that will lead you to every formula. It turns out that the reason that leads you to every formula is because for any formula like that, you can prove that this is a theorem. So if I know, so if I have two things like that are theorems, then I can use modus ponens once and get rid of that, do it again, get rid of that, and I'm stuck with just that. And that psi could be literally any formula, so that's how we know that we can get anything from there. But again, it's one of these things where it's not something you just you create. Oh, everything follows from a contradiction. First, you don't know what a contradiction is until you define it, and then depending on how you define that and define sort of what a contradiction is in your system, if it's this or if it's that or something like that, then after that, it's going to be a consequence of your rules if they are close enough to classical logic that you'll be able from there to get to anything. Again, that's all something that's sort of coming from the rules that we've created. All right, I'll definitely stop there.